Hello. Now we start chapter 18, which is called Reaction Rates and Equilibrium. We will be working on this via Educanon, and we will not be using Pearson for this section. We will be just using Educanon. So let's get started. First thing we're going to talk about is something about how can we use oxidation or rusting to cook a meal. You might have seen this in the Pearson videos that you've listened to already. You know that this will heat them, okay? These MREs will be using that. But what is it that we're using to do that? By rusting iron, magnesium, we are able to heat the food, okay? So we take advantage of rusting to create heat. So how fast does this happen? If we want to cook food on the go, we want this heat to be produced very, very quickly. For instance, if you strike a match, you see a flame, and it burns out very quickly. But what happened to the coal that is in the ground? That took millions of years to become coal. What was it before? It was plants that died and then kept on being buried by more and more dead plants and then compacted by pressure to make coal. So in the first case, the striking of a match is very, very fast, whereas the making of coal in the ground is very, very slow. So a rate, you've probably seen that term many, many times. A rate is how something changes with time. One rate that you are very familiar with, I am sure, is miles per hour. Those of you who are getting your permits and learning how to drive know that if your rate is too high in miles per hour, you may get a ticket from a policeman for speeding. So miles per hour is a rate. Meters per second. Drops per minute. Anything that you measure per unit time is a rate. So we call reaction rate the rate of a chemical reaction. So usually we say rate is the change in the amount of reactant or product per unit time. So how much reactant is used up or how much product is produced for a given amount of time. It could be seconds, it could be minutes, it could be hours, days, weeks, years, centuries. So let's look at a reaction over time. First we have just the reactants, which are the red squares. After a certain period of time, we see some blue circles appearing, which means the blue circles are a product. After more time, we even see more blue circles. Then in the second to the last box, we see two red squares left, and finally we might see one red square left, and the rest are all converted to blue. So that's basically a reaction occurring over a period of time. So if we were to look at that, we decreased our red squares from the first box to the second. We basically lost how many? We lost 4 squares. So if we look at that as about 10 minutes, we lost 4 squares of red in 10 minutes. Okay? So if we look at the next square, we now have only 4 left. So we lost how many more? We lost 3 more in 5 minutes. Then in 5 more minutes, we lost 2 more. And then in 10 more minutes, we lost 1 more. Okay? So we're looking at the rate kind of changing as time goes on. Now, what has to occur for something to happen? Well, we know we have to have a collision, okay, between two particles. Two things must collide for a reaction to occur. We also remember learning that the collision has to be oriented in the proper way. Okay, so first thing is they have to collide. They have to have enough energy that they react also. They can't just touch and maybe they won't react at all. Okay, they can just bounce apart. Kind of if like you have a pool table and you have basically hit the billiard balls and some of them will bounce away from each other when they collide and some will just stay there. So an effective collision of oxygen is the red particles and hydrogen are the grayish colored particles. So we have O2 and two H2 molecules. They collide and then all of a sudden they come apart and we've got two water molecules. Remember, I like to call that the Mickey Mouse compound. Now, the same thing could have happened, but they all go their merry way because they did not have either enough energy or they weren't in the proper orientation, so no reaction occurred. So what is that energy that we need? Okay, think of the match we talked about earlier. The match is lit by striking it against something. So that striking is enough force or energy to provide the energy for that reaction to occur. We call this the thing that activates the reaction, activation energy. So this energy is the amount that we need to get the reaction going. So there's a certain amount of energy we have to put in to get it going. So it's kind of a barrier that keeps the reactants from reacting until sufficient energy is there. Okay? So we need to put some energy in. Sometimes it's a very small amount, sometimes it's quite a bit. Okay, when the two particles collide, we saw back in that picture of the hydrogens and the oxygens meeting, kind of this activated complex where everything's kind of arranged together, but it's very unstable and it will fall apart very quickly. And so that is going to be at the height of our activation energy. Okay, so how do we get activated complex? If the colliding particles have enough energy, number one, and if the atoms are oriented properly. So if you haven't written this down, what do you need for a reaction to occur? You need particles to collide. You need them, secondly, to have enough energy when they collide, and they have to be in the proper orientation for the atoms to stay stuck together. So when they collide, they can form this activative complex. The lifetime, the amount of time that activative complex lasts is like 10 to the minus 13 seconds. That's snap that you just heard is a lot longer than 10 to the minus 13 seconds. So you can imagine how quickly that is. So in this short period of time, what happens is all the reactions form and reform, and then you've got your new products. So the activated complex, sometimes we call that the transition state. So let's look at this as a diagram for what I've just described. Okay, so if we look on the left-hand side of this picture, we see reactants, and it's at a certain amount of energy. Those things have bond energy. They have a certain amount of energy within them. So then we do something. We add energy in some way, and they kind of go up a hill. When we get to the top of the hill, we see our activated complex where everybody's kind of hanging out together. And then as we come down the hill, we've created our water molecules, and then it goes down, and at some point, we get our final energy of the products that we created. In this case, we see that the energy of the reactant started at a higher point than the one at the lower point. When that occurs, we call that an exothermic reaction. That means the energy has been released from the reactant. So if we see this right here, let me get my pen. This right here, okay, is the difference difference. And we call that delta H. Okay, so that's the difference in our reactions. All right, so the energy was released by the reaction. Okay, this here, let me change colors. Let's go to magenta. Okay, that is the activation energy. And notice it's the distance from the reactants to the top of the hill. And this here is from that to there, that's the total energy that we kind of put some more in, then we got it all back. So this part gets subtracted out when we have an exothermic reaction. Now, this picture looks similar, but we traded places, okay? We've got the water over here and we've got the free molecules over here. So they're really happy over here because when everything's bonds and the energy is lower, they're much more stable. So water is much more stable than hydrogen and oxygen. So we have to put a lot more energy in to get our activated complex. And then we have our products over here that have absorbed some of this energy. So now, if we look at what's happened, we now have our energy gained over here. You'll notice that this amount and the one in the previous slides are exactly the same, but this one is going in, the other one's coming out. So this is positive, we're putting it in. The chemicals are gaining energy, and in the other case, when we're going the other way, they would be losing energy. So exothermic is negative and endothermic is positive, okay? So that's something we're going to need to know. So endothermic absorbs the heat, exothermic releases the heat. Okay, so this idea of collision theory explains why some things are fast and some things are slow at room temperature. Okay, carbon and oxygen will react when charcoal burns, but the reaction has a high activation energy. So think about that. You have a piece of coal. Most of the time, the coal will not just ignite if you just hold a match to it. You have to have it in a certain kind of heater. But once you do, you're able to keep the coal burning because it releases enough energy to activate it each time. So if we look at the activated complex in carbon and oxygen, we have to break and rearrange those bonds during the activated complex. And at room temperatures, usually the collisions of oxygen and carbon molecules are not sufficient to break those bonds. So at room temperature, basically the reaction rate is 0 because nothing's happening. We haven't put enough energy in. We have to do something to initiate the reaction. Okay, so what factor determines whether a molecular collision results in a reaction? I'm going to stop the video for a second and we can answer this in Educanon. Let's see how you did. The molecules must collide with enough energy in order to react. The minimum amount of energy needed is called activation energy. Okay, so you have to have enough energy when the molecules collide to overcome the activation energy.